Regulate. Regulators! Mount up.
Well, good morning, good afternoon, or good evening, depending on what time of day it is that you're watching this lesson. In this video, we're going to go over vectors in the plane. But before we do that, I want to just take a moment here and read this right here. Don't watch the clock. Do what it does. Keep going. Because that's true. Don't get too concerned with time. Just keep working. Keep working. Okay? All right, now let's jump into the lesson here. It's going to be in our pre-calculus book, section 6.3 and 6.4, vectors on the plane and dot products. All right, so as a vector just gives you directions from one point to another. So here's the definition of the component form of a vector in the plane. If V is a vector in the plane whose initial point's the origin, and whose terminal point is V sub 1, V sub 2, then the component form of V is given by this right here. V is, then instead of parentheses, they use what looks like a little less than and greater than sign, V sub 1, V sub 2. The coordinates V sub 1 and V sub 2 are called the components of V. If both the initial point and the terminal point lie at the origin, then V is called the zero vector and is denoted by 0. Or 0, 0, or if you don't go anywhere. Now, whenever we want to draw a vector, if possible, we want its initial point, or the original point, to be at the origin. Okay, and then the vector, the components of the vector just pretty much tell you how far left or right to go and up or down from the origin to get there. You guys, I know what you're thinking. It's just like a point, right? Let's say this terminal point right here was the point, well, it looks like it's the point 3, 2, right? To plot a point, we start at the origin and just do what the point tells us. This would tell us to go 3 to the right and 2 up. When we put these little symbols in front of it, right, then that makes it a vector. That tells us it's some line that goes 3 to the right and 2 up. It's not just a point there hovering out there, it's actually a line there. Okay, it's got a length, or what we call magnitude, and it's got a direction. Okay, so down here we've got the definition of magnitude. Now normally they do two absolute values around V for magnitude. Some books will just do 1 around it. That means the same thing. It's the magnitude of the vector is the square root of, they do Q sub 1 minus P sub 1 squared plus Q sub 2 minus P sub 2 squared. And then that turns out to be the square root of V sub 1 squared plus V sub 2 squared. And here when they're doing Q and P, it's like they're telling you that your initial point is P and your resulting point is Q. They're just finding the distance in between 2 points. Right, it's like we're taking the second x minus the first x squared plus the second y minus the first y squared and taking the square root of it. So that right there is just like the distance formula. Okay. Now let's do some examples. It'll make more sense with examples. We want to find the component form and length of the vector V that has an initial point at 3, -7 and a terminal point at -2, 5. Okay, so if we want to picture that, we can always sketch a little picture. Okay, and they're giving us points. So the point 3, -7 would be about right here. Here's the point 3, -7. That's our initial point. We're going to the terminal point, -2, 5. So let's see, -2, 5 would be over here somewhere. -2, 5. So we've got a vector that starts right here and goes to there. And basically when we write the component form of the vector, we're telling somebody how to get from this point to that point, right? So when you've got it sketched, it's pretty easy to figure out, hey, this way we went, let's see, 3, then another 2 to the left. So we went 5 to the left, Then we went from -7 up to 5, so we went up 7 plus another 5, we went up 12. Right? That's all a vector is telling somebody. It's telling somebody how to get from the initial point to the terminal point. Right? If we want to use the formula they gave us, well, actually, we didn't have a formula here, but I can show you here. To find the component form of this vector, all we're basically doing is we're taking the terminal point, which was -2, and subtracting the x of the initial point, -3. And we're doing the same thing with the y's. The terminal point of the y was 5, and then I'll subtract the initial point, -7. So look at this. -2 minus 3 is -5, and 5 minus a -7 is 12. So really, to find the component form, you could think of it this way. If you've got an initial point and a terminal point, which back here we should have, I'm missing something here. We should have said here that the initial point was q sub 1 and the terminal point, or the initial point was q and the terminal point was p. So let's see, if we jump back here, let's say here we're given 2 points. It's almost like the distance formula here. Let's move this down. Let's say we're given the initial point as x sub 1, y sub 1. And our terminal point is x sub 2, y sub 2. All right, then to find the vector, you just find out how far it went left or right. So you take the second x minus the first x. That's your left-right component. Then to find the up-down component, you take the second y minus the first y. And that finds your component form of the vector. Okay, so this would be your initial point, and this is your terminal point. So this is where you start. This is where we started. Here's where you stop. So you take where you stopped minus where you started to find the left, right, and the up-down components. Okay. Now, if we want to find the length or the magnitude, okay, if we have the component form, which we have right here, then to find the magnitude, all you do is take the square root of the left-right magnitude squared plus the up-down magnitude squared. So I'm going to do 5 squared plus 12 squared. I'm going to ignore the negative. The negative just tells me which direction it goes. So I wind up with the square root of 25 plus 144, which would be 169. That turns out to be 13. So the magnitude of this vector is 13 units. That means if I went in a straight line, I'd only have to go 13 units. If we do it component-wise, we've got to go to the left 5, and then we've got to go up 12. If we went straight across, we would have only gone 13, right? Hey, look at that, you guys. It's like a right triangle. It's like we're using the Pythagorean theorem here. All right, now here's operations we can do with vectors. Okay, if u is u sub 1, u sub 2, that's a vector, and v is v sub 1, v sub 2, that's another vector, then the vector sum, to find u plus v, we just add the left-right components of each and the up-down components of each. We can multiply a scalar by a vector, some number c, we can just distribute it to the left, right, and the up-down. We can take the negative of a vector, we just change the signs, right? Instead of going left and up, we'd go down and right. And then we can subtract vectors. Just like we add them, we can find the difference just by subtracting the left, right, and the up-down components. Pretty straightforward. Okay, here's an answer example. Let's say vector v is -2, 5, and w is 3, 4. We want to find these. So for part A, I want to find 1/2 of vector v. Vector v is -2, 5. So half of that, I just distribute the half through here, and I get -1, 5/2. Right? You could write -1, 2.5, 2.5, any of those if you want. Okay, now for b, we want to find w minus v. So I want to take vector w, which is 3, 4, and I want to subtract vector v, which was negative 2, 5. So when I do that, all I do is I take the left rights and I do 3 minus a negative 2. And then I do the up-down components and I do 4 minus 5. And that turns out to be 3 plus 2, it turns out to be 5. And 4 minus 5 is negative 1. Now, guys, what's really going on there is we're saying here for V, you go to the left and up 5. For W, it says 3 to the right and up 4. So when we subtract these, instead of going, well, we're still going to go 3 to the right, but instead of going 2 to the left, we're going to do the opposite. We're going to do 2 more to the right. That's how we get the 5. All right, and then we were going to go 4 to the right, and then we subtract 5 to the opposite of 5 to the right, or subtract 5, go 5 to the left, and we've got, or excuse me, go up 4, and then instead of adding or going up 5 more, we go down 5, so we go negative 1. Okay. Now, for part C, we're going to take vector v, which is negative 2, 5, and we're going to add 2 times vector w, which is 3, 4. So I'm going to have negative 2, 5, and I'm going to add to that. If I distribute the 2 through here, I get 6, 8. So negative 2 plus 6 would be 4, and then 5 plus 8 would be 13. There's our resulting vector. All right, so those are some properties we could do with vectors. Here's some other properties. Okay, and these are the same things with addition and subtraction, right? We can do the cumulative property, the associative property, right? If we do u plus v, it's the same as v plus u. The order doesn't matter. We can group them differently, get the same answer. 0 plus anything is what it was. Anything plus its opposite is 0. If we do a scalar times a vector, we can multiply the 2 scalars first. If we're adding 2 scalars multiplying by a vector, we could distribute the vector to each scalar. We can distribute through a scalar, and then 1 times anything is itself, and 0 times anything is 0. And then a nice little side note here is if v is a vector and c is a scalar, then the magnitude of the scalar times the vector equals the absolute value of the magnitude times the magnitude of the vector. Okay, that comes in handy if we get big numbers with a vector. All right, so an example of that, I just made this problem up here. Here's where we'd use this little property right here. Right, if we want to find the magnitude of this vector, right, who wants, let's say this is vector v. Who wants to take the magnitude of vector v and do the square root of 72 squared plus 36 squared, right, without a calculator? You guys, again, I'm using positive 36. I'm taking the absolute value because the negative just tells me go left instead of right. See, I don't want to do that. That's going to be a big number. So why don't I take vector v and I look at it, 9 would go into both of these numbers. So I can factor out a scalar of 9 and be left with 8 and negative 4. Wow, you guys check that out. I'm even noticing now that 4 can come out of both of these. If I bring out a 4, then I'll have 36, and then my vector will be 2, negative 1. Right? If I was really astute, I would have noticed 36 went into both of these numbers. So here's vector v with the scalar pulled out. So if I want to find the magnitude of v, then I could take the scalar. If it was negative, I'd make it positive because we take the absolute value of it. And then multiply that by the magnitude of this vector, which would be 2 squared plus 1 squared. So that's going to be 4 plus 1. That's going to be 36 square root of 5. So there is the magnitude of vector v. Would have been a lot of work without a calculator, right? Pretty easy if we pull out the scalar. All right, now just to confirm that, what if I take the square root I do 72 squared plus 36 squared. And we get this decimal. Let's compare that to 36 times the square root of 5. Sam. You guys, and look at that. This would have been a big number and a lot of simplifying to get down to this. So it's really nice to know this property right here. All right, now you guys, a unit vector in the direction of v. If v is a non-zero vector in the plane, then the vector u equals v divided by the magnitude of v, or 1 over the magnitude of v times v. It has a length 1 and goes in the same direction of v. That's a unit vector. So to find a unit vector, all you do is you take a vector and divide it by its magnitude. So here's an example. Find a unit vector in the direction of v equals -2, 5, and verify that it has a length of 1. All right, well, to find the magnitude of this vector, I'm going to take the square root of 2 squared plus 5 squared. And I'm going to get the square root of 29. All right, so the unit vector for v is just going to be the left-right component, -2 over the square root of 29, and then the up-down component, which is 5, over the square root of 29. There's my unit vector. That's a vector that has a unit of 1, or a length of 1, that goes in the same direction as this vector. Now, if I wanted to verify it that had a length of 1, then I'd find the magnitude of that unit vector. So I would take the square root of 2 over the square root of 29 squared and add it to 5 over the square root of 29 squared. And look at this. I'm going to get the square root of 4 over 29 plus 25 over 29. I get the square root of 29 over 29, which is just 1. Right? So what we did is we found this unit vector. Let's think about this vector we were given. All right, we have a vector -2, 5. So let's say it starts at the origin. It's going to go to the left and 5 up. This vector is going to do that right there. We just found a unit vector that just goes from here to here and has a length of 1, right? That's what this vector right here does. It goes in the same direction, but only a length of 1. That's why they call it a unit vector. Okay, now, you guys, standard unit vectors. 1, 0, or 0, 1 are standard unit vectors. This is just a vector that goes 1 to the right and doesn't go up or down. This one doesn't go left or right, it goes 1 up. They can write them in what they call linear combinations, where just I equals 1, 0. And j equals 0, 1. So basically, I tells us left or right, j tells us up or down. Okay, and then we could do stuff like this now. Let u be the vector with initial point at 2, -5, and a terminal point at -1, 3. And let v be 2i minus 2j. Write each vector as a linear combination of I and j. All right, so you guys, a couple things here. When they tell us v is 2i minus j, whoops, the hook should have gone the other way there. 2i minus j, that's the same thing as saying it's this right here, 2 and then -1. Right? It's a vector that goes 2 to the right and 1 down. Now, we want to find vector u. So to find vector u, I'm going to take the terminal point. The left, right is -1, subtract the initial point, 2. Then for the up, downs, or the y's, I'm going to do the terminal point as 3 minus the initial point as 5. So for u, I'm going to get -3, 8, which is a linear combination. I can write -3i plus 8j. All right, so for part A here, when they ask me to write u as a linear combination of I and j, I've got it right there. It's -3i plus 8j. Now, for b, we want to write 2u minus 3v. So 2 times u, which is negative 3i plus 8j. I'll write them as a cursive. That'll look a little better to me. And then I want to subtract 3 times v. V is 2i minus j. So distribute the negative 2 or the 2 and I get negative 6i, whoops, negative 6i plus 16j. And then distribute the negative 3 and I get negative 6i plus 3j. Then combine like terms, negative 6i minus 6i would be negative 12i. And then 16j plus 3j, whoops, that was a j. 16 plus 3 would give me 19j. So there's 2u minus 3v as a linear combination of I and j. If we just want to write it in normal vector form as a linear combination, it's negative 12, 19. All right, it's telling us 12 to the left, 19 up. This says the same thing. All right, now, you guys, if u is a unit vector and theta is an angle measured clockwise from the positive x-axis to u, and the terminal point of u lies on the unit circle, right? If it's a unit vector, it's going to lie on the unit circle, and you have that u is cosine of theta, sine of theta, or the I is cosine of theta plus j is sine of theta. Look at that. Cosine goes with x, sine goes with y. Right? Moreover, it follows that any non-zero vector v making an angle theta with a positive x-axis has the same direction as u, you can write the magnitude of the vector times the cosine of theta times the sine of theta. That would give you the component form. Or if you want to write it with the i's and j's, you write it like that. All right, let's give this a shot. Vector v has a magnitude of 3 and makes an angle of 30 degrees, or pi over 6 with a positive x-axis. Let's write v as a linear combination of the unit vectors I and j. So it has a magnitude of 3, and it makes a 30-degree angle. So the x would be cosine of 30 degrees, and the y would be sine of 30 degrees. All right. And you guys, it sure is nice that we memorized this 30, 60, 90 triangle. Comes in handy, helps out a lot. Go square root of 3, 2, 1. So this is going to be 3 times cosine of 30 is square root of 3 over 2. And the sine of 30 is 1/2. So if I distribute the 3, I'll get 3 square root of 3 over 2. That's going to be I. Plus 3 times 1/2 would be 3/2 j. There's our vector. All right. Okay, now the definition of parallel vectors. Two non-zero vectors u and v are parallel if there's some scalar c such that u equals the scalar times v. All right, makes sense. So vector w has initial point 2, -1 and a terminal point -4, 7. Which of the following vectors is parallel to w? Well, first thing we got to do is put w in component form. So I'm going to do that right here. All right, I'm going to take the terminal point -4 minus the initial point for the left rights. So I'm going to do -4 minus 2. And for the up down, I'm going to do 7 minus a -1. So w is -6, 8. All right, w goes 6 to the left and 8 up. Right, now, if there's some scalar we can multiply these by to get this, then they're parallel. And if I'm thinking about u, the way I would figure this out is I'd think, okay, this left-right component is 3. Can I multiply 3 by some scalar to get -6? That was my left-right on my w. Well, yeah, if I divide by 2 or 3, c turns out to be -2. And if I do -2 times -4, I get 8. So when I multiply the up-down by the scalar, I get the up-down on the other one. So these are parallel. So this is parallel. 2 L's and 1 R. Come on, you rascal. To W. Now, if I try the same thing on this one, if I do 12 times some scalar and set that equal to -6, I'm going to get the scalar's -1/2. But if I do -1/2 times 16, I get -8. In W, it was +8. So this isn't parallel. All right? Because it also helped too sometimes if you sort of sketch, let's look at a picture of what's going on here. Whoop, I don't want that. I want just the plain line. Okay, vector W goes 6 to the left and 8 up. So it goes right there. This vector right here goes, vector U goes 3 to the right and 4 down. Whoops. So it's doing something like that. Right? And then V went 12 to the right, 16 up. That's obviously not parallel. Okay, now you may be saying, well, wait, that's the same line. No, because these aren't lines. Remember, these are vectors. And I just chose to let this vector, all these vectors, start at the origin. I could have let this vector start at the point 0, 1 if I wanted to. Right? I could see they look parallel. We proved they were parallel by finding that scalar. Okay. All right. Now, because we're doing 6,4 and 6,3 and 6,4. 6,4 here's the dot product. Okay, the dot product of a vector U and vector V, when you do the dot product, all you do is you multiply the x, y coordinates, and you multiply the left-right coordinates of both vectors and the up-down coordinates of those vectors and add them together. Okay. Now, properties of the dot product is U dot V is the same thing as V dot U. If you've got U dot V plus W, you could do U dot V and U dot W and add those together. If you have a scalar, you could do 1 times a scalar, multiply, do the dot product of the other. 0 dot product of anything is 0. And the dot product of 2 vectors is just their magnitude squared. Okay, so let's try a couple examples of this. Here's vector U, V, and W. Let's find each of the following. Okay, first, for part A, we're going to find U dot V. Well, all I do to find the dot product of 2 vectors, U and V, is I take the left-right components of both, so 2 and 5, and I multiply them, and I add to that the up-down components, -2 times 8. So I get 10 minus 16, I get -6. Okay, you guys, notice here how the dot product of 2 vectors turns out to be a scalar. Right, when you do the dot product of 2 vectors, you're going to get a scalar. Now, for part B, we want to do the dot product of U and V times W. Well, I know the dot product of U and V is -6, and then I'm going to multiply that by W, which is -4, 3. Whoops, and I should have done the little vector symbols there. So if I distribute the -6 in here, I get 24 and -18. Okay, now you guys, I think maybe I'll go back here and I'll try this product here, or this property here. Let's see what we're doing here. We're doing U dot V times W. So, well, shoot, we didn't have a property for that, so let's just stick with what we got here. All right, now for C, we're going to do U dot 2 times V. All right, so if I want to do, well, I'll work this out first. So U, I'm going to do U dot, well, let's write U out here. So U is 2, -2. I want to do the dot product with twice V. So if I double V, I'm going to get 10 and 16. So if I do the dot product, 2 times 10 is 20, plus negative 2 times 16 is negative 32. So 20 minus 32, I get negative 12. Okay, now with this one, let's check out this property right here, where it said if we had a vector and the dot product of a scalar times the vector, we can pull the scalar out front. So on this, you guys, what if I pull the scalar out front and I do 2 times u dot v? We already know u dot v is negative 6, so I'm going to have 2 times negative 6. I'm going to get negative 12. Look at that, deja vu all over again. Okay. Now for d, I want to do the magnitude of w squared. So if I find the magnitude of w, I'm going to take the square root of 4 squared plus 3 squared. All right, remember again, I ignore the negatives. That just tells me to go left. Okay, so I get the square root of 16 plus 9. I get the square root of 25, which is 5. So if I want to do the magnitude of w squared, I just add the square down there and I get 25. Okay. Now, we had a property back here that said v dot v is the magnitude of v squared. So let's see what we'd get if we did w dot w. So negative 4, 3. So if I took negative 4, 3, I did the dot product of that. Well, I'm going to do negative 4 times negative 4 is going to be 16. Plus 3 times 3 is 9. 16 plus 9, look at that, 25. Boom. All right. Now, you guys, if we want to find the angle between two vectors, if theta is the angle between two non-zero vectors u and v, then the cosine of theta is going to equal u dot v over the magnitude of u times the magnitude of v. That's a very useful formula. Okay. Now we can find the angle in between these vectors right here. So if I want to find the angle in between these two vectors, I know the cosine of that angle is going to equal u dot v. So if I do u dot v, it'll be 1 times 2 is 2, plus 1 times negative 2 is negative 2. And I put that over the magnitude of u would be the square root of 2. Remember, magnitude is just the square root of this squared plus this squared. And then times the magnitude of v is going to be 2 squared plus 2 squared. It's going to be 4 plus 4. It's going to be 8. But guys, look at this. I'm going to get the cosine of theta equals 0. Well, where does cosine equal 0? First time it equals 0 is at 90 degrees, or pi over 2. So the angle in between these two vectors is 90 degrees, or pi over 2. Okay. Now, for part B, when I do this for B, let's see, I'm going to do the cosine of theta. It's going to equal the dot product. So I'm going to do 3 times 2 is 6, plus 1 times negative 1 would be negative 1. And I put it over the magnitude of u, which would be the square root of 3 squared plus 1 squared. So 9 plus 1 would be 10. Then times the magnitude of this vector, which would be 2 squared plus 1 squared, it would be 5. So cosine of theta is going to equal 5 over, this would be the square root of 50, which, let's see, 50 is 25 times 2, so that's 5 square root of 2. So basically, we want to know, where does the cosine of theta equal 1 over square root of 2? Well, 1 over square root of 2 is, cosine of 45 degrees is 1 over square root of 2, so that's 45 degrees, or pi over 4. Okay. You guys remember too, if we were doing this on our calculator, let's see, I'm going to check my mode. I'm in radian mode, so I'm going to change this to degree. Whoop, exit out of that. Come on. So if I did inverse cosine of 1 divided by square root of 2. Look what the calculator tells me, 45 degrees. If I did inverse cosine of 0, look at that, 90 degrees. Okay. So I just showed you on the calculator because if this didn't turn out to be one of our perfect ratios or our nice ratios, you'd have to do the inverse cosine. Okay. So you want to remember the angle between two non-zero vectors. Cosine of that angle is going to be the dot product of the vectors over the product of their magnitudes. Okay. And maybe right here too, just to picture this first one. All right. Watch this right here. This first vector, I go one to the right and one up. The other vector, I go two to the right and two down. Right? That looks like a right angle. We just verified it was a right angle. All right, now, definition of orthogonal vectors. Two vectors are called orthogonal if their dot product is 0. Okay, and orthogonal means perpendicular when dealing with vectors. All right, so orthogonal means perpendicular. And you guys look at this. When we did this problem right here, the dot product turned out to be 0. And the vectors had an angle of 90 degrees in between them. They were perpendicular. So whenever the dot product turns out to be 0, two vectors are perpendicular. But when we talk about vectors, we say orthogonal. Okay? So let's determine whether these vectors right here are orthogonal, parallel, or neither. So first off, to check if they're orthogonal, I want to find their dot product. Right? So if I do 4 times 1, I get 4. 0 times 1 is 0. 4 plus 0 is 4. They're not orthogonal. Now, if I do some scalar, if I multiply 4 by a scalar to get 1, I'd have to multiply it by a fourth and I'd get 1. If I multiply 0 by a fourth, I don't get 1, so they're not parallel. So these two vectors are neither. And now here, to check these two vectors, first I'll check the dot product. 2 times 3/2 would be 3. 18 times negative 1 over 6 would be negative 3. 3 minus 3 is 0. These two vectors are orthogonal or perpendicular. Right? Orthogonal is the word they use when they're dealing with vectors to say perpendicular. The angle in between these two vectors would be 90 degrees. All right, guys, let's finish this off with one last one. This is going to be a fun one. We'll do a word problem here. Okay, and this is really going to show us what vectors are useful for. Okay, so an airplane's traveling at a fixed altitude with a negligible wind factor. Airplane's heading north 30 degrees west at a speed of 50 miles per hour. All right, so I'm going to sketch this. So here's a little northwest compass here. This plane is going north, but it's swinging 30 degrees to the west. Okay, so here's my plane. This angle right here is 30 degrees. Because instead of going due north, it swung 30 degrees to the west. Okay, now it's going at a speed of 500 miles per hour, so I'm going to let that be the magnitude of this vector, 500. I could write a nicer 500 than that. Okay, there's my plane. Okay, now as the airplane reaches a certain point, it encounters wind with a velocity of 70 miles per hour in the direction north 45 degrees east. So there's wind coming like this. And if we put it in here, the wind, instead of being due north, right, is 45 degrees to the west, or east, excuse me. So 45 would be about like that. Okay, so this angle right here is 45 degrees. And the wind's coming at 70 miles per hour, so its magnitude is 70. Right? And you guys, really, the wind's coming in like this. Okay, so if the wind comes in like that, we want to know what's the resultant speed and direction of the plane. Well, the plane's going to should wind up over here somewhere. Right? The wind's going to push it off course a little bit. We want to figure out what that is. So we want the resultant speed. That's going to be the magnitude. So let's call this vector v right here. We want to find the magnitude of v, and we want to find the direction. So we want to find this angle inside here, right? And then say instead of going north, it's being pushed, it's going that far to the west. So we know that angle is going to be less than 30. We just have to figure out what it is. All right, so you guys, what we're going to want to do is put both of these vectors that we've been giving, the plane and the wind, right? This one's the plane, this one's the wind. We want to put both of those vectors in component form. Okay. So what I want to do for the plane, maybe I'll do the plane in blue here. I'm going to go all the way from here to there. I want to figure out what that angle is. Well, it was north 30 degrees to the west, so we got 90 plus 30, that's 120 degrees. So when I do the plane here, from an earlier slide, we knew to find the component form. Let's get back here. Right here, we could take the magnitude times the cosine of the angle for the left-right times the sine of the angle for the up-down. So I'm just going to work off of that right there. Okay, so for the plane, I'm going to take the magnitude of the plane as 500. Then I'm going to do the cosine of 120 degrees, and then the sine of 120 degrees. That will give me the left, right, and up-down components of the plane. For the wind, I'm going to take the magnitude of the wind, which is 70. I'm going to do the same thing. If this is 45, then this angle right here is 45. So I'll take the cosine of 45 degrees times the sine of 45 degrees. Okay. Now, because when you do this, when you have vectors in component form, you can add them together. So the resultant thing here, resultant vector is going to be this. I'm going to take, right here, 500 times the cosine of 120, and I'm going to add to that 70 times the cosine of 45. There's the resultant left-right direction or component of the plane after the wind pushes on it. Negative 200.503. Negative 200.503. Okay. Now, define the same thing, but for the wind, I'll do the exact same thing here, but I'll change cosine to sine. Or I shouldn't say for the wind, for the up-down component. So I'll change cosine to sine. I'll get 482.510. 482.510. 482.510. Now, if I want to look at that on a compass bearing here, maybe I'll sketch it in here. Plane is going exactly like we thought it would. It's going something about like that. Okay. We need to find the magnitude of this, and we need to find this angle right here. Okay. The easiest thing to find is the magnitude, and the magnitude would be the speed of the plane. Right. So the speed is going to equal the magnitude of that vector. Well, because all we have to do to find the magnitude of that vector is take the square root of the left-right component, so 200.503 squared plus the up-down component, which was what, 482.51 squared. Boom, there's the speed of the plane, 522.511 miles per hour. 522.511 miles per hour. So because the wind is really, as the wind comes in and pushes on the plane, it's speeding it up, right? It was going 500 miles per hour, but the wind's now making it go 522 miles per hour. Okay, now to find this angle here is, if you think about this, if we made a triangle here, we just went 200.503 to the left, we went 482.51 up, right? I could find this angle inside the triangle right here with tangent. The tangent of A would be 482.51 divided by 200.503. So let's do that. Let's find out what angle A is. Let's do inverse tangent of 482.51 divided by 200.503. You guys notice I ignored the negative. The negative just tells me direction. All right, so this angle A right inside here turns out to be 67.435 degrees. Okay, we want this angle right here. So we want to say, instead of going north, the plane's going that far to the west. So let's take 90 minus that. So 22.565 degrees. And you know what, you guys, let's do this. Let's put it in degrees, minutes, seconds. Let's go into here, convert to degrees, minutes, seconds. 22 degrees, 33 minutes, 54 seconds. So 22, so the plane's going north, then 22 degrees, what was that, 33 minutes, 54 seconds, 33 minutes, 54 seconds to the west. Boom. So, as it was going 30 degrees north, 30 degrees west, the wind blew it off course by about 7.5 degrees, right? So it's going to have to make up for it, but it's going faster. All right, because these vectors are new, so you just need to practice them. You need to do the homework. You can go on the internet and look up things. Do the homework, ask questions, and most of all, endeavor to persevere.